So let's continue with the video here. So now we are moving to AC circuits. So AC circuits is when you have a source and it's going to look like this. The voltage and current is varying with time. One time the current goes this way, a time later it goes this way, it keeps alternating back and forth. So this is represented with a sine wave over here, both the current and voltage. You can also write this as V sine omega t, because 2 pi f is the angular frequency, how quickly it's rotating here or alternating. And if you have an alternating circuit, then you need to be able to find the max and RMS voltage slash current. So if you're given the equation, you should be able to recognize that the number in front here is the maximum voltage. This will be the maximum current. So you don't have to calculate those. They would be given right here in the equation. Or if you are told that you have a alternating current and you're told that you have the RMS value and you want to convert it to a maximum value, so this one you can put a little knot here is the maximum value, then you would just multiply the RMS by the square root of 2 and use this equation to convert back and forth between the two. So this does mean that we did not talk about RL circuits, so you don't have to worry about this one here. Now we do have inductors that we talked about, so these are the solenoids in your circuit, and this is what they do. You have a current that's trying to form in the circuit, trying to flow, and the inductor, which is a solenoid, it produces a back EMF to oppose that current that's trying to flow. And the back EMF, or self-inductance of that inductor, the faster that the current is trying to increase or decrease, the more back EMF is going to be created or induced, and it depends on L, which is the inductance of your inductor. And because it's a solenoid, you can have the geometric properties of it here, the area of that solenoid, the number of turns, the length, and you can actually get a number for the inductance of that inductor. So the last thing is when you have all three together in a circuit, an RLC circuit, then this is where the rest of these equations are used for. And we did not cover transformers, so don't worry about that for this time. So first of all, we talked about Eli the Iceman is just to help us remember that you got the voltage and you've got the current, and they're not necessarily in phase. So maybe that this is the current in the circuit and maybe this is the voltage across the inductor, and they're not in phase. They don't peak at the same time, right? If this were the resistor, they would peak at the same time. They're in phase. But for an inductor L, the voltage, the EMF, peaks before the current. So that means that if this were an inductor, that voltage would peak before the current. And you can look at your pictures in your notes to get, because I'm not drawing it very well, because here it already looks like they're in phase, but I'm just trying to show the voltage comes before the current. And for the capacitor, the current leads the voltage. So if you have an RLC circuit, then you're probably going to need to calculate some of these values here. The inductive reactance, think of it as the resistance of the inductor. And the capacitive reactance, think of it as the resistance of the capacitor. To calculate them, you need to know omega, which you are either given F in the problem. It says, hey, you have a 60 hertz then that means you're given f, and then you can do 2 pi f to get the omega. Or if you're given the equation, then you can just get omega from whatever's in front of t. You can calculate these two. And having the reactances allow you to figure out, well, what's the voltage across my inductor, the current times the inductive reactance, etc. If you want the voltage across the resistor, then that's just going to be the regular IR. But if you want the voltage across the inductor or capacitor, you have to use the reactances. And then this one right here relates the voltage that you're getting from the source. So again, we have an RLC circuit. We have an alternating source. This is what we have here. So how much voltage that you're getting here is this one right here, and the current through the circuit, and the impedance, which you can calculate with this equation, gives you kind of the net resistance of the circuit. What's the impeding effect of all these three devices? So really these problems here are just kind of plug and chug, but just make sure that if you're not given the current in the circuits, then you need to find the impedance so that you can find the current. Now if you're given the current, then you can find the voltages across the devices by just using Ohm's law. And the last thing is the resonant frequency. So this is the frequency that you can adjust your source to in order to have the maximum current possible. So the current, if you look at this equation here, V equals IZ, that means I is delta V over Z. Right? The current is limited by the impedance. And the impedance depends on the resistance and the two reactances. So all you need to know is that if you want to maximize the current and minimize the impedance, that means you want all of this to be equal to 0. And that means that Z will equal R. And that will be the minimum impedance, and that will give you the maximum current. In order for that to happen, then the two reactances must equal each other. And when you set these two reactances equal to each other, you can solve for that resonant frequency that gave you that maximum current in the first place.